Okay, we are now moving into 8.6, talking about powers of complex numbers. So we're going to look at how we use de Moivre's theorem to find powers of complex numbers. So he's a French mathematician that found a way using a polar form of a complex number to multiply an expression like this, 1 minus 2i raised to the fifth power. Now, in the past, using algebra, basically raising something to the fifth power means you just multiply it all by itself that many times. So you write it down 5 times, multiply. So then we have to use a FOIL process to multiply 2 of them together, and then we multiply that result with the next one, and then with the next one, and so on. So it can be a little tedious and take quite a while. It actually takes less time using the polar form, so that's what we're going to be looking at. So let's first develop that process. So we'll take a look at a couple of them that don't take too long to multiply out. We're also going to use our multiplication rules from last video to come up with the pattern that we use, which happens to be de Moivre's theorem. So if we do r cis alpha raised to the second power, so that means you're multiplying it by itself. Because this is being multiplied using that multiplying rule that we learned last time, we would multiply the two r's together, and we would add the alphas. So it would look like this. Simplified, it would be r squared cis 2 alpha. Now we're going to take a look at r to the third. Well, r cis alpha to the third, which is just r cis alpha squared times another r cis alpha. So we're going to use what we came up with in the previous part here, the r squared cis 2 alpha, and multiply that with r cis alpha, again using our multiplication rule. So we're going to multiply these two parts together. Using that multiplication rule, you would multiply r squared times r, and then you would add 2 alpha plus alpha. And we get r cubed cis 3 alpha. Hopefully you're starting to recognize a pattern. We're going to do one more, r cis alpha to the fourth power, to confirm if we see a pattern happening, if it actually happens with r cis alpha to the fourth. So that's just r cis alpha to the third times r cis alpha. Remember, the cis means cosine plus I sine of that value. So r cis alpha to the third is what we came up with in the previous part, r cubed cis 3 alpha. Multiply it with one more to get it raised to the fourth power. So using our multiplication rules, we get r to the fourth cis 4 alpha. So anytime you are raising a polar form number to a power, you would take your coefficient, raise the coefficient to that power, and then you're going to multiply the angle measurement by that power. So it's 4 times alpha and r raised to the fourth power. So the general rule is this. So if z is equal to r cis theta, you can use a theta or an alpha, then z to the n power is r to the n power cis n times theta. So that is our de Moivre's theorem. So de Moivre's theorem and the Argon's diagram together can show some pretty interesting patterns. So we are going to explore some of that. We'll do one practice where we're just raising a complex number to a power using de Moivre's. And then we're going to look at some of these patterns that are developed using the Argon diagram to graph the powers that we come up with. Also remember, at any time you can pause the video if you wanted to write anything down into some notes so they were easier for you to reference later, or going back and re-listening to something I may have said before. And if you have any questions, please write them down as you're watching the video so that you can ask me through email later and I can answer those. All right, so first we're just going to do a basic practice where we have -1 minus I raised to the third power. And we're going to use de Moivre's theorem to help us multiply that out. So the first thing we want to do is convert it to polar form. And remember, polar form is the same as saying trigonometric form. Our book uses one of them, and I've seen the other one on like the LBCC exam before. So just making sure that we're familiar with both. So we would first convert it. So remember, to find r, you do x squared plus y squared and then square root it. Remember, the x is the real part of the complex number, so it's this -1. And the y is the imaginary coefficient for the imaginary part of the number. So that'd be -1 as well. So then we get the square root for r. Theta, the inverse tangent of y over x. Make sure you remember to check your quadrant so that you're getting the correct angle measurement. Tangent is positive in 2 quadrants, quadrant 1 and quadrant 3. So you want to make sure that you get the correct measurement for the inverse tangent of a +1. And since it was a negative y and a negative x to start with, that puts us in quadrant 3. So it would be 225 degrees. Now we're going to use de Moivre's. So I'm raising, this is the polar form, square root of 2 cis 225 degrees, raised to the 3rd power. So I take my coefficient, square root of 2, raise it to the 3rd, and then cis 3 times 225 degrees. So then simplify that. I actually do the raising it to the power and the multiplying. Then one thing to note is that we always want this angle measurement to be a number between 0 and 360. So then I have to find the equivalent angle measurement to 675 that is between 0 and 360. So I subtract 360 until I get to a number, positive value, that is between 0 and 360. So 675 degrees is the equivalent to 315 degrees. If I do the sine of 315, I get the exact same answer as if I do the sine of 675. So this is our polar form of that number raised to the 3rd power. But since we had started in a regular rectangular form, complex number, I'm going to go ahead and find out what that value would be. So we expand the cis part. So that means cosine of 315 degrees plus I sine of 315 degrees. And then you're going to multiply that result by 2 square root 2. So don't forget, we have to remember that unit circle. That's going to keep coming up. And so cosine of 315 degrees is square root of 2 over 2. And the sine of 315 degrees is negative square root of 2 over 2. And then distribute the 2 square root 2 into the parentheses, and you get 2 minus 2i. So that is the rectangular standard form of that value. So that is how we use de Moivre's. Now let's see how it connects to the Argonne diagram and some of these interesting patterns that develop. All right, so this is the problem. So these are listed as some explorations. So z equals 1/2 plus square root of 3 over 2i. And we want to find z to the 2nd, z to the 3rd, z to the 4th, z to the 5th, and z to the 6th. And then we're going to plot them on an Argonne diagram. So the first thing we need to do is convert this to our polar form. Up here in the upper right-hand corner, I have the reminder, what is de Moivre's and how we use it. So we first convert to polar form. So I calculate r. So it's the x squared plus y squared, and then take the square root. So we end up getting a 1. And the theta would be inverse tangent of square root of 3 over 2 divided by 1/2. That's the y over x, which happens to be 60 degrees. So you can also sketch your triangles with these values to help out in identifying which quadrant and angle measurement we would have. So I do the regular z. Z is this number that we started with. We started with 1/2 plus square root of 3 over 2i. Converted to polar form is 1 times cis 60 degrees. And again, you can think about what the cosine of 60 degrees is and the sine of 60 degrees and convert it back, and that's what we started with. So we want to make sure we write, after we get the polar form, we want to write it back in to regular standard complex number form or rectangular form. So we'll have it in both formats. So now we're going to do z squared. And this is where the de Moivre's theorem comes into play. So we're going to take the 1 and square it, and take the 60 degrees and multiply by 2. Then we convert it to rectangular form. So 1 squared is just 1. So we're going to do cosine of 120 degrees, which is negative 1/2, and the sine of 120 degrees, which is the square root of 3/2 times I. So this is our rectangular form of that same number. And then we do it with z to the third. So 1 to the third power, cis, and then you do 3 times 60, which is 180 degrees. And then calculate cosine of 180 degrees, sine of 180 degrees. We get negative 1 plus 0i, which is technically just negative 1. So we'll show again how that looks on a diagram, the Argand diagram. If you have a different number here in front, instead of like 1 to the third power, if it was 2 to the third power and you had an 8, then you would have to multiply each of these by 8. You would have to remember to distribute that in. And we're going to look at an example later of that. All right, and so I'm just going to get rid of this. Maybe. All right, so then we have z to the fourth, z to the fifth, and z to the sixth. So you can always pause the video, double check, make sure you understand how I'm getting these rectangular form numbers and the polar form numbers. Now what we're going to do is look at the graph of each of these. So I'm going to first graph z, which is 1/2. So I'd go 1/2. I'm looking at this as a unit circle, so 1/2. So this would be 1 all the way out to the circle. Half would be in the middle. Square root of 3/2 would be here. Think of your 60-degree angle. And so we end up with this vector representing z. Doing z squared, we'd go negative 1/2 and square root of 3. So then I'd have a net vector going in that direction. This one was negative 1 plus 0i. So that just goes out negative 1 in this direction. Negative 1/2 negative square root of 3/2. So a vector in this direction in the third quadrant. Whoops. There we go. And then z to the fifth and z to the sixth. So you draw each of those in there. And then you look at the pattern that develops. It creates a hexagon. So one of the things to know as we're looking at these patterns is to look at this coefficient. And then we'll have a summary slide about these coefficients and how it determines what kind of a diagram we're going to have. All right, let's look at a couple other examples and some of those patterns. So this one is z equals 1 plus I. Again, convert to polar form. So we go through the process of converting to polar form. And so we get z is equal to square root of 2 cis 45 degrees, which is 1 plus I. Now we're going to do z squared. So we square the square root of 2, which gives us just 2. And then we multiply 45 degrees by 2, and we get 90 degrees. And then we convert that back to our rectangular form. So cosine of 90 degrees is 0. Sine of 90 degrees is 1. Don't forget I have to multiply by that 2 in the front. So I get 0 plus 2i. If it helps you to show more steps, you can show more steps. In this case, I haven't. We should be very familiar with the unit circle, so I can get that number, and then just don't forget to multiply by the 1 in the front. Then we're doing the square root of 2 to the third power, so that's 2 square root of 2. Cis 135 degrees, that was 3 times 45. And so we get negative 2 plus 2i. So then you go through and do the rest of the powers, the 4, 5, and 6. And then we're going to graph those. So the first one is 1 plus I. So I would go over 1 and then up 1i, so I get this vector. The next one is just 2i. So remember, that's just going to be on this vertical axis. And there's 2i. -2 plus 2i. So we're going to have a vector that goes right through there. The next one is just -4. -4 goes in the horizontal axis to the left. -4 plus -4i would be this vector. And then -8i is this vector right here. So then we get this pattern. If you notice, the vectors get longer and longer as we go. We have created a spiral that spirals out. Okay. Again, note at this number here in the front. If you recall from the previous slide, it was a 1 all the way down, 1, 1, 1, 1, 1, and we had a polygon. This one, we have a number that's bigger than 1 and gets bigger and bigger and bigger, and it spirals out. Now, let's take a look at another example where we have 1/2 plus 1/2 I. So again, same process, convert to polar form. So we get square root of 2 divided by 2, cis 45 degrees. Do the squared using your Demoivre's to calculate that value and then convert it to rectangular form. So it would be square root of 2 over 2 to the second power and 2 times 45 degrees for your angle measurement, and then convert it. So I'm just going to show the rest here. So we do z to the third, z to the fourth, z to the fifth, and z to the sixth. Notice these coefficients. These are all less than 1. Okay, they're all numbers that are smaller than 1. So let's graph them and see what happens. So I have 1/2 plus 1/2 I. Notice my scale. It doesn't go out to 1 like the circle did on the previous slide. And the one on the top was scaled 1, 2, 3, 4, 5 all the way around. So this one I had to go a smaller scale. So I went 0.25 to 0.5 because all of these numbers get smaller. So 1/2 plus 1/2 I. So I go to 1/2, 1/2 I get a vector that goes out that direction. Okay, so there's my vector. 0 plus 1/2 I, so I'll have one on this vertical axis. -1/4 plus 1/4, so -1/4 plus 1/4. I'm going to have this vector right here. I feel like I missed a vector. Oh, that's a positive 1/4 I did, that one. Okay, so the -1/4, positive 1/4 goes up. So we have that vector. We have the -1/4. This is the -1/8, -1/8, and then just -1/8 I. So this one started way out here and it spirals in. Okay. So it's a spiral that spirals in. There it goes, spirals in. So when we have numbers that are bigger than 1, it spirals out. When we have numbers that are less than 1, it spirals in. And when we have numbers that are exactly 1, with the unit circle, they eventually start repeating themselves. Okay, so the powers remain on the unit circle and they just start to repeat themselves. So the greater than 1 counterclockwise spirals out, less than 1 spirals into the origin. And so then here's just some pictures of where we see these spirals in nature. So this one is an elephant with his tusk wrapped around, his trunk wrapped around his tusk, creates a spiral in. You have a hurricane, which spirals. The nautilus shell, which also spirals. Okay. So just some examples where we see these spirals in nature that are related to these complex numbers. So that is the lesson on powers of complex numbers. If you have any questions, please let me know. This is going to be the assignment that goes along with it. So page 796, you'll do numbers 2, 6, 7, 8, 11, and 12. If you have any questions, please let me know.